So we are continuing the workshop on the theme of pre-processing, pre-solving, reformulation, with a talk by Andy Oertel on MIP-based pre-solving. Please.
Yes, so yeah, I will tell you a bit about like the recent advancements in like certifying operations research, and especially like pre-solving. Like it's pretty similar to what Hannes talked about in the first session with the pre-processing in Maxat. And this is joint work with Ambrose Gelijksner, Alexander Höhn, and Jörg Nordström, and will be presented next week at CPI Award. So what is 0-1 integer linear programming? So we're given an objective function that we want to minimize. And this has integer coefficients. And then we're given a collection of linear inequalities. They also have integer coefficients and integer right-hand sides. And our variables on domain 0-1. And so we want, well, so our goal is we want to minimize, like we want to find the optimal value for this objective function subject to satisfying all these inequalities. And then you think like, okay, why this problem? Why do you study this? And then maybe we have to look a bit like in the future to our grand goal of like certifying mixed integer linear programming, where we then have real valued coefficients. We can have variables that are integers or real values, like any crazy stuff. And well, this is actually a problem that is very relevant in practice. Like you can model a lot of different things with MIP. Like it's daily used to solve real world problems in logistics, scheduling, whatsoever. And it turns out that 0-1 integer linear programming is a very nice special case where you can already test and like experiment and figure out a lot of reasoning techniques used in MIP. So that's why we study as a first step to get to MIP 0-1 ILPs. So before, just I thought you're okay, we have like a problem, we have a solver and get a result. But that's actually not the full picture for like state-of-the-art solving. What we actually do as a first step, we have a pre-solver. This pre-solver manipulates, changes our problem, and gives us a pre-solved ILP, and then this problem is fed to the solver. So, and this is also known as pre-processing in like Maxat or in other communities. And when you think about like, okay, pre-solving, why should we care? Do we even need this? Well, it's actually like when we look at like a results from a paper by Achterberg et al. They investigated like the performance of pre-solving techniques, and it turns out that like with pre-solving, like on average, they solve MIP instances like 3.3 times faster, and especially for larger instances that take a while, the speed up with pre-solving is quite a lot. And they, as a conclusion, they say that like pre-solving is like one of the most important heuristics in mixed integer programming. So it's really, really important to them. So yeah, what we do, like we want to do, we want to certify this 0 integer linear programming solving. And when we look at the preliminary work, then, well, for these solvers, there has been developed already this Viper proof system, which is based on like branch and cut certificates. And well, we can use this to certify a solver, or we could also use VeriPB. Like, for example, you could equip rounding sets or SAT4J with VeriPB proofs and get a certificate from the solver. The only thing that's missing is then this pre-solver. And when we look at Viper, for example, then it's pretty much based on these branch and cut certificates. So it does not understand anything about like the reasoning that is done in these pre-solvers. So this will not work, and the way we fix this is we do a proof logging in pseudo-Boolean reasoning, and then we can verify these proofs with VeriPB, and then like with both certificates for both tools, we get a complete certification of the solving process. So yeah, that's first before we get to proof logging. Let's take a quick step back. Like you heard this over and over again. But like just for like getting you all on the same page, we have variables that are Boolean, so they have 0 and 1. Literals are either the variable or its negation, And the negation is just simply like 1 minus the variable. Then a pseudo-Boolean constraint is just an integer linear inequality over these literals, like this one. And then any like constraints, like any of these inequalities in the 0, 1 ILP is just a pseudo-Boolean constraint. So these are equivalent definitions. You might have to syntactically change them because like integer linear programming people are operations research people, they don't like literals. They all have their variables all non-negated. Whereas like we are happy with like negations and so on.
And they always use less than or equal, right?
Depends.
It depends.
MIP people do minimization greater or equal, whereas like linear programming people do maximization. Yeah, it's always whatever your canonical form is. And then we also will use in this talk equality constraints, which is just a shorthand for two inequalities. Then our proof system is based on the cutting planes proof system. So we have linear literal axioms. We can always just say that our variables are between 0 and 1. We can add two inequalities. We can multiply them by a positive integer. And we can divide by a positive integer. And then we can do this trick of rounding up because all of this is just integers. Then what we will also need is strengthening rules, because like this pre-processing, it will remove solutions, it might add solutions, but mostly it will remove solutions. And the main strengthening rule that we will use is the redundance-based strengthening, like you heard about it quite a bit in the last talks. So we have to give a substitution which maps variables to truth values for literals. And then we have to show that this implication holds. So that like from our formula and the negated clause constraint, we can derive, or we can derive that formula and the constraint we want to derive holds under witness, and our witness does not make our objective worse. And yeah, and both of this, like the objective, this witness, like this substitution, omega, it has to be given explicitly, and this implication, it should be like easy to check, which it can either be like some reverse unipropagation, or some look up in the database, or you give it a subproof, basically. You basically have to give like an explicit proof. And what is this strengthening rule, the redundance-based strengthening, useful for? Well, you can do symmetry breaking stuff, like simple symmetry breaking with this redundance-based strengthening. You can do without loss of generality reasoning, or you can introduce extension variables if you want. And well, just as notes, there's this additional strengthening rule, this redundance-based, this dominance-based strengthening, which I will not require for this talk. So just as a note, it also exists. Then one thing we have to be careful about in especially optimization problems is deletion. Like we cannot just arbitrarily delete constraints, as then like when we delete constraints, we introduce more solutions. And when we introduce more solutions, well, then it could happen that one of these solutions is better than the optimal solution to our original problem. So yeah, we cannot just do this arbitrarily. We have to restrict deletions. And also when it comes to the dominance rule, the dominance, like deletions are unsound when we just delete arbitrarily when we have the dominance rule. So we have to somehow restrict like how we can delete. And the way to do this is that we have like these two sets of constraints where we have this derived set where like, yeah, this is things that are implied derived from our formula, and like we don't have any obligations to that set. We don't commit to the set as like, yeah, being relevant in that sense, that we can just rederive it at any point. So. And from these sets, from the derived set, we can just delete at any point. We don't have to care about it. But what is relevant is the core set, this other set, where we commit like, okay, this is equivalent, this core set is equivalent to our original formula. And from this set, we can only delete a constraint if it can be rederived by redundance-based strengthening from like the rest of the core set without this constraint. So we have to show that we can rederive it, otherwise we cannot delete it. Then the final rule I will talk about that we need is objective updates. And the idea is that, well, you will change your objective. So you change your objective from f old to f new. And the check that you have to do is basically that you have to show that the old objective is equal to the new objective. And this has to be implied by your constraints. So your constraints have to restrict this equivalence. And then we had like two ideas. Like we had the first idea, well, you derive a new object, you want to change to a new objective. So the obvious idea to us was, well, just introduce the new objective, just name the new objective, write it down. But then we noticed that like if we have big objectives and we only do small changes, then we're writing down this large objective over and over and over again, which just blows up the proof. And so it turns out this was maybe not the best idea. Like it can be a good idea if you do big changes. Like if you have your huge objective and you just want to derive now, oh yeah, my objective is equal to 4.
Do you mean a huge objective in terms of like loads of variables in it?
Yeah, exactly. Many variables, and when you just want to change it like to a constant, then this would still be like a good idea to use this specifying of the new objective. But what actually turned out to be for our application better is that we just give the difference between the new objective and the old objective. And then you can basically add this difference to your old objective, which gives you the new objective. So, and then you only basically specify this change. And then you're thinking, okay, well, why do you introduce new rules all the time? Can't we just live with our old rules? And here's some like justification why we introduced objective updates. So for one, it like naturally represents the reasoning done in the solvers and especially this presolver. Like you basically, when you're doing these objective changes in the presolver, then the presolver at some point, it fixes a variable to some constant, and then you want to remove this variable from like your objective and your constraints. And then if you always have like your objective still talking about this variable, that's like, you always have to keep around basically this fixing, and you want to avoid this. Like you want to really represent the reasoning that is done by the solver, presolver. Another thing that is, well, was the very convincing reason for us also was that substitutions for this redundance-based strengthening become very complicated and almost impossible to do without this objective update. Like I have here a small example. Like we start out with this problem. And here we basically have this constraint. Here basically just says that x1, x2 is equal to x3, x4 plus 1. So we can use this equality to rewrite or to change the objective to this problem. And now, if we would do redundance-based strengthening, now we can see like here, oh yeah, our x2, it's like not restricted by the objective, and it does not hurt us to set x2 to true. Like we can just, without a lot of generality, we can set x2 to true with this witness. But then if we still have this old objective around, then we have as a proof obligation that we have to prove like that the objective does not get worse. And proving this, well, this comes very complicated. And yeah, this is only a small example. And then at some point you have to keep track like of all your changes and whatever. And like, it just becomes a lot of bookkeeping. And you don't want to do this. And so we just went the easy way and introduced a new rule that naturally represents like what the solver is doing, and we're fine with it. Yes, and with that, so this is how the proof system looks. So how can we certify pre-solving with it? Well, the pre-solving reasoning, it will change the objective, it will change the problem over time. And so that will change the solution space over and over. But the good thing is like our proof system is sound. So it does guarantee that like anything we derive has the same optimal value as like our original problem. So all the steps in our derivation, every time we have the same optimal value. So the only thing that we have to do at the end is then to check that like the constraints that we derived that are in our database at the end of the proof is equivalent to the pre-solved theorem, like to the pre-solved problem that is outputted by the pre-solver. And this you basically just do by checking equivalence, like check one by one if like a constraint for every constraint that is in the derived problem, you check does it exist in a pre-solved problem and vice versa. And then you check that the objectives are equivalent, like exactly the same syntactically, nothing magic. And yeah, what you get as guarantee is that then the original problem has the same optimal value as the pre-solved problem, except for like if you log solutions and introduce improving constraints, solution improving constraints, because like they will like reduce, like they will shrink your solution space, and especially if you log the optimal solution, then you will not have any solution, so you will not have the same optimal value. But like the tool detects this and handles this and outputs you, oh yeah, I've certified equivalence, equi-optimality up to like logging this solution. Yeah, and then, well, I will not go into detail about like all the rules and steps that are done in pre-solvers, but let me just go through like a small example so that we can see like what reasoning is done, or like what is done in these pre-solvers and how we can justify it. So first rule, like we are starting with this problem, and then one rule is growing. So the pre-solver will just set a variable to like a fixed value and then do unit propagations or bounce propagations, they call it in MIP. And if this reaches a conflict, then the variable has to be set to the opposite value. So for example, like it detects that x3 has to be 1 because setting x3 to 0 leads to a conflict by propagation. The nice thing is here, like we have this reverse unit propagation rule, so we can just introduce x3 by reverse unit propagation, and then we can eliminate this, like this variable is now fixed, so we can eliminate it from like all the constraints, and this we just do by addition, like adding this new constraint, and literal axioms, like depending on which polarity we have, and as a result we get then this problem here, where like in the original constraints that we had before, the x3 is removed, and we now have that x3 is set to 1. As the next step, we would like to rewrite the objective. We change the objective, like we now know that x3 is 1. So we would also like to change this in the objective, and then we can actually remove x3 from our constraints. And yeah, as I just told you, we have this objective update rule that we can use directly. So we can specify the updates, and we have this as a proof obligation, which just solves by like this x3 being greater equal 1. And then at the end, like we have the objective does no longer talk about x3, and all these constraints no longer talk about x3. So we can just remove x3 we can just delete x3, and we have to give the substitution that x3 is 1. And then as the last thing, like we can do a dominated variable. So for example, here with a sort of generality, x1 will always be larger than x2, because like in the constraints, x1 has always at least the coefficient of x2, and in the objective, the coefficient of x1 is at most the coefficient of x2. So it's always better to set x1 to a higher value, as this would like satisfy our constraints more, and it would like give us a better objective value. And the way we can do this is, well, we just use this redundant space strengthening. We give as a witness that they are like mapping onto each other. So x1 goes to x2 and x2 to x1. And then we can introduce this relation that x1 is greater than, that x1 is less than or equal, greater than or equal x2 by this constraint, which, yeah, basically expresses this. And add this to our problem, and now we have like broken somewhat of like a symmetry between these two variables. Yes, and well, that's sort of a theory, and now we like also implemented this in this, yeah, state-of-the-art like integer linear programming presolver Papilo, which was like parallelized and highly optimized and whatever. It's like in this skip optimization suite. And we added like pseudo-Boolean proof logging to it. And then the proofs that were generated, we checked them with VeriPB, our proof checker.
Work in the parallelized version?
Yes.
And then what are you doing to your proof?
The thing is, like how Papilo does this parallelization, it does like try a lot of techniques on like, it has a fixed problem that it starts with. And then it tries a lot of techniques in parallel. But it does not apply them. It just tries the transactions basically. And then it keeps track of like transactions that it could do, like that would be valid with this current problem. And then it linearly goes through like these transactions, like in a sequential step to check, oh yeah, can I do this transaction? And while doing this transaction, by doing this change, this is all sequential, it will write a proof. Like there's no proof in the parallel step, basically.
But it's true that one somehow future feature that has not come up for some reason is parallel proof logging and parallel proof checking, because this will definitely be an issue here at some point.
Yeah, tricky without lots of generality reasoning.
Yes.
Nobody said life should be easy.
Exactly. And then we use as benchmarks the optimization decision instances from the pseudo-Boolean pseudo-Boolean competition 2016, and from the MIP library where like the instances have been translated to OPP. Yeah, the first thing we wanted to know is like how much does it slow down Papilo? And so here's a table, like we have decision instances, optimization instances. Like this is how many instances we had. And this is like the average mean, geometric mean running time. And well, we are a bit like everything above 1 is basically the like how much it is slower. So we're like somewhat like 40%, 30% here slower, which is more than like we would like to have. But yeah, the comparativity comes from this thing that like these transactions are tried in parallel, and then but this proof is written in sequential. So like it will slow down the sequential step, which is which is slowing down the solver the most, or the pre-solver the most.
And what are these numbers? These are these shifted geometric means?
Yes, shifted, this is shifted geometric mean by shifted by 1 second. So this is seconds shifted by 1. Yes. Yeah, and then as a next step, we were interested in like, okay, how long does checking need? Like here are some plots, like this is for the PB16 instances, and this is for the MIP instances. And then you can see it's not looking too good. Like this line here, that would be like linear scaling, like we have a overhead factor 1. And this line here is like a factor 1000. So we're between a factor 1 and 1000, and a lot of instances are like around here of like factor 100 overhead. So like this plot is like, basically seems like it's all over the place checking. And when we look like at like the averages, the data, when we like compute the means, then like we're okay, we're like 20 times slower, something like this. And it doesn't look too good when you think about it. Like if we're aiming like for like 10 times or whatever, something like this in that range. But well, when we look at the instances or like the results, well, okay, we have at least the result that most of the instances are checked within 10,000 seconds. But also they are pre-solved within like a few seconds. So that's not telling us a lot. but like we have some reasons or like ideas why the proof checking compared to the solving, pre-solving is quite slow. Like one is that Papilo has more context. What I mean with this is that Papilo knows like I cannot just delete this constraint because like, yeah, like I know that there is this reason here, but I don't do like a redundancy check. Whereas like the VeriPB has to do the redundancy check in full. And it also like for any other reasoning, like Papilo just knows, yeah, I can do the substitution, I can do this, and yeah, and it doesn't have to, like, it does not justify it as much. Like, in some sense, VeriPB is almost too powerful for like what it does. Like, it needs, like, if the rules, like, in many times, the rules are like only used in a very specific manner. So if you would restrict the rules to like only do like specific things, specific checks, you could probably do the speed up the check, but then, yeah, you need this context.
And can the context not be somehow given inside subproofs? Or, I mean, if Papio has enough information to see I can delete this, then where does it get this information, and why can we not transfer it to VeriPB?
Yeah, it knows this information, but it's like it does not check it. Like it does not do the full check of redundancy.
No, but how did it figure it out? Like, if Papio can figure it out like very locally, I have this information, I know I can delete this. So why can we not transfer this information that, well,
yeah, right, we do it in the best way, but
is
still,
part of this simply the difference between knowing and actually proving?
yes, exactly. So like Papilo just knows from like it's doing pre-solving, it knows that like it can delete but like the correctness of like the algorithm, like basically when you're proving the correctness of the algorithm that it does, like you implicitly know, okay, it will like not change or like it will not introduce new solutions, but it does not prove this, like it does not figure this out. It just knows this like from like the way the algorithm works.
okay. But then, I mean, I would expect this to be some sort of local information that you're not changing too much by this deletion, or that there is a presence of another. I mean, there should be something in the algorithm that guarantees, right? And then the question is, yeah, how can we explicitly?
Yeah, that's a good question. And like we thought about this, and yeah, we did not come up with like a nice like, yeah, just do the subproof and it will work. Like very often it was that especially when you want to do substitutions, like you don't want to introduce a lot of like temporary constraints that are not needed for later. You just want to, yeah, obviously like I have these two constraints, I just want to rewrite it.
What happens if you compare these times to like the solver time that you need after that to solve it? Because then the overhead shouldn't look that bad.
Yeah, that's like, okay, we haven't run experiments on that, but yes, the solver time will be way much more than like the pre-solving time.
Wouldn't we expect the preprocessor to be like the most highly efficient part where like the overhead would be the worst?
Exactly. No, exactly. That's also, I think that's like, yeah, that the preprocessor is just like very quick and it will produce a lot of proof for you.
Did you try running a non-parallelized version of Papio?
Yeah, and it was like 2 times, something like this, not even, like was below 2 times. Factor 2. Because it's basically just like you're just getting like this figuring out the transactions, but that's like in either way, in the sequential way and the parallel way, that's like the thing that you not spend a lot of time on. So most time is spent in the sequential part, a lot of time. So. Yes, and then another thing that, like I showed you like this probing, for example, where we do like these redundant, reverse unit propagation steps. We do reasoning based on unit propagation, and we also tried like we noticed that like these RUP steps were taking quite a while, And well, what they are in practice, reverse unit propagations, they are just shorthand for like simple cutting planes derivations. So why do we not just write down these cutting planes derivations, and maybe that's faster? And we also run experiments on that, and it's a bit faster, but probably not as much as we hope for. Like it's only a few percent that's improving our performance. But yeah, that would be like a thing to, like we also have now this reverse unit propagation with hints, like in LRED. And now it would be also interesting to see if this would improve the numbers even more as like preliminary results on that hint towards better performance.
Did you do this manually or using Oertel?
Manually. We did this manually, like this in Papillo. Papillo supports like outputs of these in route or in cutting planes. Yeah, and so for conclusion, yeah, 0-1 integer linear programming seems like a good first step towards like mixed integer programming certification. Then our the pre-solving, as we see, as you saw, is like very important part for MIP, and we show that we can do a certification of pre-solving with pseudo-Boolean proof logging, with like which adds to the list of a lot of things. Probably that's definitely not complete that we already can do with pseudo-Boolean proof logging. And as future research directions, like I mentioned already, that we want that like this wrap with hints would be interesting to try out for this performance. And then like doing proof logging, like automated planning. Then, well, there's mixed integer programming. There has been a paper, an archive paper last year by which like theoretically thinks about like how can this proof system that we have here with redundance be extended to general integers and floating points or real numbers. And then, yeah, dynamic programming would be a nice thing and other combinatorial problems. And we would also like to have certification for enumeration and counting problems. And with that, thank you, and that's all.
Any additional questions for Andy while perhaps the next speaker mentally starts preparing for setting up? Did they ask all questions already? And let's thank Andy again.